Welcome back to the live classroom of my teacher sessions. We were in the process of discussing the concepts of nuclear energy release or nuclear energy and release of energy by a process called nuclear fission. So nucleus is it has got a tremendous amount of energy inside. So we can harness it by one of the processes called nuclear fission reaction, which was basically used initially for the atomic bomb explosion and all, which was an unfortunate incident happened in Hiroshima and Nagasaki. So now we will just go through the basics about what we discussed today before we get into the actual harnessing of energy with the help of nuclear reactors. Just have a look at this. Watch this PPT. The world is facing energy crisis. We are always in search of newer energy sources. The center of atom is called nucleus. According to Einstein, the mass m is equivalent to an amount of energy, E is equal to mc squared. This is what we have seen, and Otto Hahn is the well-known scientist who was given Nobel Prize for the discovery of nuclear invention of nuclear reaction, nuclear fission, for which only he was awarded Nobel Prize in 1944. And you know, as the result of nuclear bombing or atomic bombing, it created lots of destruction over there in Hiroshima and Nagasaki. We have seen that. Further, the large nucleus is bombarded with a particle. This is nuclear fission. The small particle is what is neutron. The nucleus splits into smaller nuclei and several neutrons, and large amount of energy are released. Okay, a large amount of energy is released. These are the things which we have discussed already. And an example also we have just mentioned. An unstable nucleus of uranium-236 is formed when uranium-235 is bombarded with a neutron. Then it will split into krypton-91 and barium-142, and it would release more neutrons as well. So then further we said about the chain reaction, which says that when one neutron is used for bombarding a nucleus, it will release more neutrons and it will further release a lot of energy by splitting more and more nuclei. Now let us see what happens in a nuclear power plant. So in a nuclear power plant, we are controlling the nuclear fission reaction. Okay, otherwise the chain reaction is being controlled in a nuclear nuclear power plant. Okay, so now what we will observe is, I'll show you the case of controlling nuclear fission reaction or chain reaction with the help of a reactor. Okay, so remember, I'll brief you something about that. We have seen the concepts of chain reaction, and the chain reaction is causing a lot of energy released as a result of the process. But what happens is, you know, there are certain terms to understand about the controlled chain reaction. The first thing, you know, the neutrons, when it is being released, so it may gain a lot of energy on the way. But remember, ideal particle for fission is slow moving neutrons. You know, if the neutrons are going very fast, it may not be absorbed inside the nucleus, the chain reaction would not proceed. So on the way, if you want to make the neutrons cause fission reaction, the speed of the neutrons to be controlled. Otherwise, such neutrons, such slow moving neutrons, are generally termed as thermal neutrons. So these thermal neutrons we have to make on the way, if at all during the chain reaction, if the neutrons are gaining more and more energy, we have to reduce the speed, for which we will use a specific material, and is called moderators. So moderators are the substances used to slow down the neutrons. You know, heavy water is a typical example of moderator, and your heavy water, you must be familiar with the D2O, you know, with the help of deuterium instead of hydrogen. Such heavy water can be used to make a moderator, and graphite is another substance which is also helpful for reducing the speed of fast moving neutrons. Another one is, you know, about, suppose we want to control the reaction. This is a major thing. Like, you know, if more neutrons are causing fission reaction, more energy will be released. But on the way, during the release of energy, we want to absorb those neutrons. We don't want some neutrons to cause fission reaction. Okay, so for which we will make use of a device called control rods. You know, the substances like cadmium and boron, it will be able to absorb the excess neutrons. So if you want to reduce the rate of reaction, rate of amount of energy released, we have to use control rods. You just watch this simulation, which will help you to understand what is the role of a control rod. Watch this. See, I'll show you the simulation of, one second. I hope it is clear. Yes. Okay. Now I hope you can see this. Okay, this is the working of a nuclear reactor. Just how control rod is being utilized. You can, one thing we can see, the right side you can see two bars. This indicates the power output and energy produced. Okay, and just I'm going to fire a neutrons here. Let's see what's happening. So I fired a neutron. Some reaction is produced over here, chain reaction, that released, see, this much amount of energy. You know, the green bar, you can see this much amount of energy is released there. But now I am resetting the nucleus again. Further I am using, see, this is, these rods are called control rods. Okay, so I am pulling the control rods out. I hope you have seen this. Control rod is pulled out, okay, partially. Then again I am firing the neutrons. Just observe what is happening. See, this is leading to more reactions. You know, chain reaction keeps going. So by adjusting the control rods, you can see clearly lot of energy is released. You know, the green bar is very high. So lot of energy is released during the reaction. Okay. So now if I am pulling the control rods maximum in, that means the rate of reaction is very much low. This is the lowest possible amount of energy released. And if it is taken out completely, now let's see how, if you fire the neutrons here, the energy released will be tremendously high. So a large amount of energy would be released here, which shows that it is uncontrolled. So if the control rods are pulled back, pulled down, maximum, you see on the screen, see the energy released is too high. You know, the very big amount of energy is released with the reaction of fission reaction. Okay, but this is surely what to say, with the help of the control rods, surely we would be able to control the rate of reaction. This is how we control the amount of chain reaction. But again, this situation, that is about the controlling of chain reaction, controlling of chain reaction is what is being done over here. And in addition to that, you suppose this is the there is a core. First of all, in a reactor there should be a core inside which this fuel is to be kept. Again, when you say about nuclear fuel, we said uranium-235 is what is actually used for the fission. Even plutonium-239 is useful for fission. But you know, the naturally occurring uranium, it is not suitable, the majority of the uranium is not suitable for fission. So the very first thing we are going to do is convert non-fissionable material to fissionable, non-fissionable to fissionable. For that to be possible, we have a process called enrichment. So the uranium which is to be used as a fuel should initially be enriched before we keep it inside the core of the reactor. Okay, inside the reactor, before keeping it in the core, we are going to enrich the uranium. That means that process is called enrichment. So what's the meaning of enrichment? It is the conversion of non-fissionable material to fissionable material. So in India, we have, especially in Tamil Nadu, you might have heard of the place Kalpakkam, we have a nuclear power plant there. It was actually the first of its kind in the world. Okay, we were the one initially, you planted this kind of a reactor, fast breeder reactor, you might have heard of. So fast breeder reactor, actually what happened is, inside the fast breeder reactor, the importance of that is we would need to just feed only or give only the normal uranium. The naturally occurring uranium you can give it to it. But inside the reactor, in addition to the reaction taking place, it also converts non-fissionable to fissionable. That is the the enrichment process also is what is being done in such a reactor. Okay, so that is what is the importance of fast breeder reactors. So such a uranium or enriched material we will put as the fuel. Then inside the fuel I mentioned about the control rods and all. Okay, so these control rods are further converting these control rods are controlling the rate of reaction. And here what happens is there is a material which is called a liquid sodium, otherwise a coolant is what is fed into it. You know, this coolant is what is actually absorbing the amount of heat released from it. So the coolant absorbs the heat released from the core and that will be taken out. So the heat is being absorbed from inside the coolant, and this is what is actually happening in a nuclear reactor. So once again, in core the chain reaction happens, the fuel is kept in the core, chain reaction happens, and the large amount of energy is released, and this heat is being absorbed by taking the coolant given to it. That coolant is coming out as very hot liquid, and this heat is what is being utilized to boil water to produce steam and to rotate the turbine and production of electricity and all. Okay, I think it would be better you just watch the one of the videos that will surely indicate how a reactor works. Okay, just watch this video.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation, as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So, a nuclear reactor successfully generates nuclear energy from fission reactions.
Hope you understood the working of a nuclear reactor. So, nuclear reactor is therefore a device which controls nuclear energy, nuclear fission for useful purposes. That is, with the help of the nuclear chain reaction only, even we are using this, but at the same time it is important that we are to take safety measures for developing nuclear energy. See, actually the reason for this is, you might have heard of the tsunami, and as the consequence of that we had the disaster happen in Japan. There the very harmful nuclear radiations came out of the nuclear power plant, but still if we have adequate safety measures on these, definitely we would be able to produce or harness the nuclear energy for useful purposes, which definitely is the need of the hour, because day to day we are, or day by day we are using more and more energy resources, due to which we are moving towards a big energy crisis. So, the harnessing nuclear energy, always you think in this way, that is nuclear fission, the amount of energy released is very large, and when it becomes chain reaction, tremendous high amount of energy is released. If it can be used for useful purposes, surely it is a big gain to the human kind, right? So, human mankind. But at the same time, you might have heard of the Chernobyl massacre, which again was a nuclear accident because of problems in the safety measures. So, you may watch this video, a short video, 1 minute video only, which will give you an idea about what exactly happened in Chernobyl. Okay. So, 1 second. Yes, this was what you have seen is a very big disaster happened in Chernobyl, which was as the result of the nuclear accident happened in a nuclear power plant. But besides this, using energy for useful purposes should definitely be encouraged, and which should definitely be a solution to all the energy crisis what has been happening across the globe. With this note, today's class, I hope all of you have enjoyed the presentation of today's session, and you have seen the videos and some details about the nuclear fission reaction. Now you explore more on the harnessing nuclear energy for peaceful purposes in different countries. We are always in need of a lot of energy as a solution to energy crisis. So, in various parts of, even in India, we have lots of nuclear power plants. So, we have to look into more and more newer sources of energy. And as far as grade 12 students concerned, remember this is a content which are definitely relevant for the board examinations. and you have to learn how energy is released in a chain reaction, and what's the difference between atom bomb, principle of atom bomb, and nuclear reactor. Atom bomb, it is uncontrolled, and nuclear reactor, obviously it is controlled. But there is one more nuclear reaction called nuclear fusion process. You can have a look at that as well in the textbook and see, and you can search for more and more on nuclear fusion reaction and explore more. I am giving it to you as a food for thought. You go more on the next nuclear reaction as well, that is nuclear fusion, and find out more. Okay, with this I am going to wind up today's live classroom or live class. We will see again with another topic, and obviously if you have any questions, surely you can contact us as well, so we will be able to discuss more on this aspect. Enjoy your days coming up as well with examinations and preparations. Okay, so see you again. That's it for today. Thank you.